If you're familiar with high-pressure sodium lamps, you've probably heard of lamps like this, and you may even have some. What are known as standby high-pressure sodium lamps, these employ a pair, thank you toilet, of discharge tubes that are wired in parallel, so that way if one discharge tube goes out, the other one can restrike. There are two reasons that this will happen. The first, and more common typically over the life of the lamp, is due to momentary supply interruptions will cause the lit arc tube to extinguish. When the electricity comes back, the comparatively cool arc tube will strike up immediately, and thus the fixture will start producing light again. Because unless the fixture is fitted with something like this, which is an instant restrike igniter, it'll take several minutes for the hot discharge tube to cool down enough for the arc to strike again. And besides being not screamingly common, these igniters are also limited in the types of ballast they can be used with. This one is only suitable for use with choke or reactor type ballasts, basically series inductor, or high leakage reactance autotransformer type ballasts. It is not suitable for use with constant power autotransformer ballasts. And of course this particular igniter requires an auxiliary power supply, in this case 120 volts, which would be derived either from the 120 volt supply or from the 120 volt tap on a multi-tap ballast if the fixture is running on something other than 120 volts. And of course, the second reason for the extra discharge tube is that when one of the discharge tubes starts cycling because it's reached end of life, the other discharge tube will take over immediately, and that's why these lamps are rated for well over 40,000 hours of burn life compared to 24,000 hours for decent quality high-pressure sodium lamps. So, again, very reliable, last a very long time, a lot better than a lot of LED rubbish nowadays. Of course, one problem with these is in fixtures that employ precision optics, the beam is going to change depending on which discharge tube is lit. And depending on the design of the fixture, it can be a fairly considerable difference. And, of course, onto the subject of this video. Venture Lighting, at least, I don't know of any other companies that made these, did the same thing for metal halide. Although, due to the operating characteristics of metal halide lamps, you only get the first of the two benefits. And that's largely why these lamps exist, which is, in the event of a momentary supply interruption, the lamp will start producing light immediately. The reason that you don't get that service life gain necessarily with these metal halide lamps is because of the electrical characteristics of the aging of the discharge tubes in metal halide versus high-pressure sodium lamps. Due to the way high-pressure sodium lamps operate, the mercury component of the discharge tube dose becomes more predominant over the service life of the lamp as sodium gets consumed either through leaking out through the discharge tube or by reacting with the aluminum oxide envelope of the discharge tube. And because the mercury plasma has a much higher resistivity, the net effect, or than the sodium, the net effect of this is that the operating potential of the discharge tube goes up over the life of the lamp. And when the ballast is no longer able to supply that potential to keep the discharge lit, the lamp starts cycling. Metal halide doesn't really do that, barring problems like hydrogen contamination, because the hydrogen that can get loose in these lamps, because the discharge tube wall is made of quartz. Quartz is permeable to hydrogen. And that's actually one of the reasons why lamps have getters like that. Those metal strip things in there with that kind of coating on them. That is going to be or at least a part of it that's relevant for the hydrogen is a mixture of zirconium and aluminum that reacts with the hydrogen and keeps it from interfering with the discharge in the discharge tube. However, barring a problem like that, which is indicative of a defective lamp, the discharge potential over the life of the lamp remains more or less constant. So the only way that you could really get an extended life out of these lamps is in applications where the lamp is being burned continuously, and every day or every couple of days having a deliberate de-energization momentarily of the fixture, so that way the cool discharge tube is going to strike. If you do that reliably, or your lighting control system does that reliably, then yes, you can get an extended service life out of these lamps. But especially because these are quartz discharge tube metal halide lamps, one common characteristic of these is because of how corrosive the halide dose plasma is to the quartz, over time it eats away at the discharge tube wall, and if it gets too thin, because the lamp has been burned, or the discharge tube I should say, has been burned for longer than its rated service life, it grenades. And so one of those discharge tubes fails, the lamp's going to explode and probably destroy the other discharge tube in the process. So really these are for applications where instant restrike is critical. But yeah, very interesting bit of lighting history there.